Four corners. Building bridges. David Glover. Three kinds of bridges. Throughout history, people have built bridges. Think about the bridges you have seen. Did you ever wonder how they stood so tall or stretched so far? Did you ever wonder how they could hold so many cars, trains, and people? Building safe, strong bridges takes careful planning. Engineers are the people who plan and build bridges. They spend a lot of time designing bridges and studying the successes and mistakes of the past. This book looks at 3 great bridges. Each was built using a different design form: arch, cantilever, and suspension. In this book you can read about how the bridges were built and why they work. Traffic passes over the Golden Gate Bridge in California. In the United States. The Leonardo Bridge, an arch bridge. In 1502, a famous Italian inventor and artist, Leonardo da Vinci, drew a simple sketch of a beautiful bridge with an arch shape. He designed the bridge for Sultan Bajazet II, a ruler of the Ottoman Empire. The Sultan wanted a bridge to cross a stretch of water called the Golden Horn in what is now Istanbul, Turkey. Leonardo wanted to create a bridge that would allow tall sailing ships to pass underneath without having to lower their masts. He began with the idea of the Roman arch. However, Leonardo did not follow the traditional arch design. He created a new type of arch bridge. Leonardo's original bridge design. How an arch bridge works. In an arch bridge, the weight is carried from the top to the ground. The strong base supports the bricks. The force of all the weight squeezes the bricks tightly together. The red arrows below show the directions in which the forces move. An arch bridge is usually much stronger than a straight bridge made of the same material. Arch bridge. Leonardo's idea was to use a single arch, made of granite, to span the entire width of the Golden Horn. The bridge was to be 220 meters long. Its highest point was to be 36 meters above the water. The bridge would have been the greatest stone arch ever built. Leonardo used mathematics to work out whether the bridge would be strong enough. The bridge was to be narrow and light at the top and much wider at its bases. As the weight of the bridge pressed down, the wide bases would spread the load over a large area. Leonardo calculated that the arch would withstand great pressure. The Sultan and his advisors were doubtful when they saw Leonardo's design. They believed that the arch would collapse. The Sultan refused to try Leonardo's idea, so the bridge was never built. This painting shows how Leonardo's bridge might have looked if it had been built. The bridge in the background is an older kind of arch bridge. Almost 500 years later, a Norwegian artist, Vebjørn Sand, saw a model of the arch bridge Leonardo had designed. The model was on display in Stockholm, Sweden, at a show featuring Leonardo's inventions. Sand was impressed by Leonardo's bridge design. He thought it was beautiful and clever. Vebjørn Sand was inspired by Leonardo's design of an arch bridge. Vebjørn Sand beside a model of the bridge Leonardo had planned. Leonardo, the inventor. As a scientist and inventor, Leonardo was fascinated by many things. He had many ideas that were far ahead of his time. Some things he designed were clocks, cranes, water pumps, a diving suit, a retractable bridge, a robot, a flying machine, a bicycle, a helicopter, and an automobile. Leonardo's flying machine. Sand wanted to try to build the bridge. It would be the first time in history that one of Leonardo's bridge designs was to be built for public use. When Sand told the Norwegian officials what he wanted to do, he convinced them to support his idea. Sand worked with engineers to check the design. They used computers to make calculations that were impossible when Leonardo was alive. After studying the calculations, they decided a full-size stone bridge would not be strong enough for modern traffic. Sydney Harbour Bridge. The bridge over Sydney Harbour, Australia, uses a single arch design. This bridge is one of the world's longest arch bridges. The bridge took 8 years to build. It was officially opened in March 1932 and carries 2 railway lines and 8 lanes of traffic. Almost 49,000 tons of steel and 6 million rivets were used in its construction. Work on the bridge began in 2001. This photograph shows the center arch being put into place. How the bridge was built. After the walkway and the center arch were put into position, the first side arch was added. A crane helped to move each of the side arches into position. Workers installed the railings on the walkway. The railings were made of stainless steel and another type of timber. The engineers decided to build a smaller version of the bridge out of timber. The bridge was to have a span of about 100 meters. Leonardo's stone bridge would have been more than twice as long. The timber used for the bridge was to be a special type laminated pine. This kind of material is made by gluing thin strips of pine together. This lamination process creates a strong, solid material. On October 31, 2001, in a small town near Norway's capital city of Oslo, the Leonardo Bridge opened for pedestrians and cyclists. A version of Leonardo's bridge had finally been built, 500 years after his drawing was made. Vebjorn Sand says that Leonardo's bridge is the perfect blend of art and function. Now, Sand's dream is to build a Leonardo bridge on every continent. Bridge facts. Name, Leonardo Bridge. Type, arch. Location, Norway. Date completed, 2001. Building material, timber. Total length, 135 m. Span length, 100 m. Height, 8 meters. This view of the Leonardo Bridge shows the partly completed bridge before the walkway railings were added. The fourth bridge, a cantilever bridge. In the 1880s, Benjamin Baker, an English engineer, and his partner, John Fowler, were asked to design the fourth rail bridge in Scotland. The design was very important. A huge storm in 1879 caused the collapse of the Tay rail bridge. Because of this accident, people were afraid of railway bridges, and Baker needed to find a new way to build the bridge. Baker decided to build a cantilever bridge. He chose steel as the building material because it was strong enough to support the weight of a train. The collapse of the Tay rail bridge over the Tay River in Scotland on December 28, 1879 was one of the worst bridge disasters in history. Benjamin Baker used this demonstration to convince people that the bridge would work. The fourth bridge was the greatest bridge engineering project of the 1800s. Construction began early in 1883. The bridge was designed with 3 huge steel towers. The towers were to rest on piers in the river and on land. The builders floated huge drums called caissons into the river. They weighted them down until they rested on the river bed. From inside the caissons, workers dug down 27 meters. When they hit bedrock, the caissons were filled with thousands of tons of concrete, then granite blocks were laid on top. Caissons were used to build the underwater foundations of the bridge. How a cantilever bridge works. A cantilever is a beam supported at one end only, like a diving board. In a cantilever bridge, 2 or more towers are anchored at their base to piers. Each tower has 2 cantilevers built out from its sides. The cantilevers can be joined together in the middle of the bridge and support a suspended span. Anchor tower. Tower. Suspended span. Cantilevers. Pier. Deck. Cantilever bridge. By 1887, the 3 steel towers had been built up from the piers. Then the difficult task of building the cantilevers began. The fourth bridge cantilevers were to stretch out like arms on opposite sides of each tower. Then 2 suspended spans would rest on the cantilever arms to link the 3 towers together. By September 1889, the cantilever arms were almost touching. Workers used cages to assemble some of the bigger parts of the bridge. Each of the 3 steel towers rests on 4 piers. Making the final connection was not easy. Metal expands in the heat and contracts, or shrinks, in the cold. The weather was very cold when workers tried to connect the last parts. The metal had contracted, and the two pieces of bridge were several centimeters apart, and the pieces could not be bolted together. The engineers decided to wrap the beams in cotton, soak them with oil, and set them on fire. The heat caused the steel beams to expand. Slowly, the cantilevers moved towards each other until the final connection could be made. Many skilled steel workers were employed in building the bridge. The bridge's two suspended spans were built after the cantilevers were in place. In early March 1890, the bridge was completed. The Prince of Wales, Queen Victoria's oldest son, hammered the final rivet into place and opened the bridge. There was a big celebration. The fourth bridge is very strong. Some of its steel tubes are 3.7 meters in diameter. This bridge was the first great bridge to be built from steel. Each of the main spans is 521 meters long, much longer than any span built before. The bridge held the world record for the longest spans for more than 30 years. The fourth bridge was built in 7 years and carries 2 train lines across the Forth River. This drawing shows the Prince of Wales at the bridge's grand opening. Today, 200 trains cross the bridge every day. It is still one of the strongest, safest, and most expensive bridges ever built. It cost millions of dollars to build and still takes millions of dollars a year to maintain. No sooner has it been repainted than it is time to begin the job all over again. New kinds of paint, though, may make this job easier in the future. Bridge facts. Name, Forth Bridge. Type of bridge, cantilever. Location, Scotland. Date completed, 1890. Building material, steel. Length, 2.5 kilometers. Longest span between towers, 521 m. Tower height, 104 meters. Deck height, 46 meters. The Akashi Kaikyo Bridge, a suspension bridge. On January 17, 1995, a terrible earthquake struck the region around Kobe, Japan. Buildings fell to the ground. Not far from the center of the quake, a great bridge was under construction. Its foundations had been laid, its 2 towers built, and 2 giant cables had been stretched between the towers. The only part of the job left was to hang, or suspend, the roadway from the cables. After the earthquake, engineers were afraid that the partly finished bridge would be badly damaged. Amazingly, they discovered that the structure was unharmed. The Akashi Kaikyo Bridge has the longest span of any bridge in the world. The Akashi Kaikyo Bridge was being built to connect Kobe and Awaji Island. When they began in 1988, the engineers knew that earthquakes were common in the area. They needed a design that could survive a strong quake. The bridge was also being built over the Akashi Strait, a busy shipping channel. Therefore, engineers wanted a bridge that would not block shipping traffic. They chose a suspension bridge for the task. The center of the earthquake was on Awaji Island, close to Kobe and the Akashi Kaikyo Bridge. How a suspension bridge works. The roadway, or deck, is suspended by hangers from cables that are anchored at each end of the bridge. The cables run across 1 or more towers and transfer the weight of the bridge to the top of the towers. The ground underneath the towers holds all the weight. The large anchor blocks at the ends of the bridge keep the cables from pulling out. Anchor block. Cable. Hanger. Tower. Deck. Suspension bridge. The engineers chose the sites for the 2 steel towers that would support the bridge. Huge caissons were towed to the sites, weighted down and filled with concrete. These became the giant piers on which the towers would stand. A helicopter strung a guide rope from one side of the bridge to the other so that the bridge's cables could be installed. The cables were made from bundles of steel wire, woven together in rope-like strands. Each wire was about the thickness of a pencil and extremely strong. There were 830 of these wires in each cable. Stretched end to end, the wires could circle the world 7 times. Normally, a large boat would string the guide rope, but for this bridge a helicopter was used. Steel cable. Wire. Bundles of wire. Each cable was made from 290 bundles of 127 steel wires. Each wire is strong enough to support 3 tons. The steel cables were threaded, bundle by bundle, over the tops of the towers. The ends of each bundle were attached to huge concrete anchors set into the ground at both ends of the bridge. By 1994, the main cables were complete and work on suspending the roadway began. Soon after, the earthquake struck. As a result of shifts in the ground caused by the quake, the distance of the bridge was stretched an additional 91 centimeters. The span would now be even longer than planned. The huge cables were made of new, high-strength wire. Workers paved the roadway, which has room for 6 lanes of traffic. The engineers continued their work without a problem. The suspended roadway was built using a truss system, a series of braces with triangle shapes that support the road from underneath. These open braces allow winds to blow through the structure without harming it. The truss system. Top of roadway. Braces. A truss system of triangular braces below the roadway provides strength and stiffness. The Akashi Kaikyo Bridge is very strong. It can withstand 290 km/h winds. It can also withstand an earthquake that measures up to 8.5 on the Richter scale. The Great Bridge was finally completed and opened to traffic in April 1998. Today, the 6-lane highway is the longest suspension bridge span in the world. It stretches 4 kilometers across the Akashi Strait. The bridge is the longest, tallest, and most expensive suspension bridge ever built. Bridge facts. Name: Akashi Kaikyo Bridge. Type: suspension. Location: Japan. Date completed: 1998. Building material: steel. Length: 4 kilometers. Longest span: 2 kilometers. Deck height: 97 meters. Tower height: 283 meters. The Akashi Kaikyo Bridge has a special lighting system that can produce many different colors. Wonders of engineering. Bridges such as the Leonardo, the Fourth, and the Akashi Kaikyo demonstrate the way engineers have used different designs to build bridges. The different designs accomplished a common goal, making safe, useful, and beautiful bridges over areas that would be hard to cross otherwise. These bridges are wonders of engineering designed and built to suit their specific purposes. The Leonardo Bridge, Norway. The Forth Bridge, Scotland. The Akashi Kaikyo Bridge, Japan. Glossary. Anchored, secured, and supported. Arch, a curving shape that is used to give bridges and buildings strength. Beam, a straight length of steel, concrete, or timber used to build bridges, buildings, and other structures. Caissons, large, hollow drums used to build underwater and to create underwater foundations or piers. Cantilever, a beam supported at only one end that carries a load at the other end or along the length of the beam. Engineers, people who plan, design, and build such things as machines, roads, and bridges. Force, a push or a pull on an object. Load, the force that a structure must support. The load on a bridge includes the weight of the traffic that crosses it and the weight of the bridge itself. Piers, solid supports on which the structure of a bridge rests. Richter scale, a set of numbers used to measure the magnitude or strength of an earthquake. Rivets, special bolts used to fasten 2 pieces of metal. Span, to connect 2 points with a section of bridge, the length between 2 supports. Suspension bridge, a type of bridge that is hung or suspended from thick cables or chains strung from towers. Truss, beams or rods put together to form a triangular, rigid support.